Good morning, everyone. I'd like to welcome everyone who's watching us at the centers, as well as those of you who are watching us here at headquarters, to our ARMD, Aeronautics Research Mission Directorate, Aeronautical Technical Seminar. We've got a really good topic today. Our speaker is Dr. Gene Morelli. He's from NASA's Langley Research Center. The seminar topic is the quest for onboard real-time characterization of aircraft stability and control. Dr. Morelli is a senior research engineer in the Dynamic Systems and Control branch at Langley. He has more than 20 years of experience in the field of aircraft system identification, which includes experiment design, data analysis, flight dynamics, and mathematical modeling based on experimental data. Dr. Morelli has designed experiments and developed models for a wide variety of aircraft, including the X-29, the X-31, the F-15 Active, the Twin Otter, the X-43A, and many subscale aircraft. He is co-author of the textbook entitled Aircraft System Identification, Theory and Practice, and he's the author of System Identification Programs for Aircraft, otherwise known as SIDPAC. It's a collection of programs written in MATLAB to solve aircraft system identification problems. SIDPAC is a NASA software product containing over 200 programs and is currently in use at more than 60 organizations worldwide. Dr. Morelli has written more than 50 technical publications, and he is an associate fellow of the AIAA. Please join me in welcoming Dr. Gene Morelli. Thank you.
Thank you. Thank you, Dr. Porter. Good morning, everyone. I appreciate the opportunity to be here today and give this technical presentation. And I want to thank the senior leadership here at NASA headquarters for inviting me to come here, providing this opportunity to talk about the research, and more generally for having these seminars on a fairly regular basis, because I think they're very useful, very worthwhile. So my topic today is the quest for real-time onboard characterization of aircraft stability and control. And I titled this as the quest for that because right at the moment we are not there. But the technology is such that we can see that we have a limited capability to do this at the present time. But the technology is there, and the goal of full envelope and all-time characterization of stability and control of the aircraft is in sight over the next few hurdles. Now, of course, there are ground-based ways to characterize the aircraft stability and control, such as computational fluid dynamics and wind tunnel testing. But my discussion here today will be about doing this in flight and onboard the aircraft using onboard measurements on the aircraft. So, and I'd like to try to give you an idea of some of the benefits, practical benefits of doing that, and some of the technical challenges ahead. So, next slide, please. Here's an outline of my talk. I'll just start with some background and some history on this particular topic, and I'll go through some technical problems, some of which we have solutions to and some which we don't. I have some flight test video and some demonstrations to show you as well, and finally some concluding remarks. Next slide, please. The topic area that covers this problem of determining aircraft stability and control, or determining a model of a physical system from measured inputs and outputs, is called system identification. And our system that I'll be discussing here is the aircraft, the rigid body aircraft, in fact, is what I'll be talking about, although it does not have to be rigid. And the idea is that given measurements of inputs and outputs to a physical system, we'd like to infer or determine what the mathematical model would be of that system that could behave in an equivalent way, or mimic the system's behavior in some way. Now, for an aircraft, the input there are multiple. We have more than one input, of course, and the inputs are generally control surface deflections. So we might have stabulator deflection and canard deflection on this particular aircraft. And the outputs are responses like vertical acceleration and pitch rate, angle of attack, and so on. Now, it's not necessary that the system be the airframe of the aircraft. That's what I'll be talking about today, because that's what's relevant to aircraft stability and control. But it could be the system identification can be applied to an actuator, for example, or to an engine. But we're going to talk about an aircraft rigid body in this talk. So, next slide, please. So, system identification is really one of three general problems in dynamics, and as shown in this slide, we have again the input to the system, which in our case is the aircraft, and the outputs, which are, as I mentioned before, and the system is the aircraft itself. And for simulation problems, what we do is we know the inputs because we have measured them from a pilot, and we have a model of the aircraft, and we predict the outputs. For the control problem, we have outputs that we'd like the aircraft, we have a way we like the aircraft to behave. We have a model of the system, and we compute the inputs. And system identification is sometimes called the third problem, or the inverse problem, where we have measurements of the inputs and the outputs, and we try to determine what the model of the physical system is. So you can see from this slide, too, that the importance of identification to simulation and control, because the output of identification is a model of the system, which, of course, both simulation and control are required to do their job. And I'm talking at a high level here, of course. So, next slide, please. I tried to minimize the number of equations I present, but sometimes I just couldn't get around it. What I have here are Newton's second law for translational motion of the CG and for rotational motion about the CG, and they're written in vector form. So, three-dimensional vector on the top line and also on the second line. The MA part of F equals MA is on the left side of these equations. If you'll just look at the top line there, so we have MA on the left, and of course we know the form of these equations. We have for many years. But what we don't know are things on the right side. So, for example, we do know the force is due to gravity and can characterize that. Very often we do ground tests for the engine, so we also have the propulsion forces. And also for stability and control, a lot of times the propulsion is not moved dynamically. So what we'll do is have a model for the propulsion from these ground tests that we'll use. And then that leaves one last term, which is the forcing function, the aerodynamic forcing functions. So that's also, the same can be applied to that second equation. We need the aerodynamic forcing function for this equation in order to fill it all out and be able to do simulation and control work. Now, the difficulty, of course, is that there's not, at the present time, an analytical way to do that, aside from computational fluid dynamics, which is still not quite to the level it needs to be to do all those problems. So we want to characterize that experimentally, and what I want to talk about here is how to do that on board the aircraft in real time. And one of the things that I've tried to get across with this notation also is that the aerodynamic forces and moments are nonlinear functions of multiple variables. That the speed of the aircraft through the air, flow angles, angular rates, and control surface deflections, and so on. So it's multivariable, nonlinear in general. And we'd like to characterize that. So for measurements of the inputs and outputs, we need to find models for those forcing functions, what I'm calling F arrow and M arrow for the forces and moments. So next slide, please. Well, as I mentioned, the forces and moments are nonlinear functions of the variables. What I've done here is just simplified it way down. Said I'll only take a look at the lift coefficient, non-dimensional lift coefficient, so non-dimensional aerodynamic force is a function of angle of attack, and that's all. Of course, it's a function of more than just angle of attack, but this is just for demonstration purposes I'm showing this. And you see the familiar character, a nonlinear character of the lift coefficient with angle of attack where there's a stall brake, a certain angle of attack. So this is a nonlinear dependency between the lift coefficient and angle of attack. But one way to describe that is to describe it as in local areas of angle of attack as linear approximations. And you can see that in the aggregate, if I look at all those linear functions together, I can describe very well the nonlinear character of that curve. So I keep the same model form, if you will, that the lift coefficient is a linear function of alpha, but I let the slope, or the CL alpha sometimes it's called, the slope of that dependency change, depending on where I am locally in angle of attack. So this, by the way, is real data from an F-16 wind tunnel test. So, and in fact, I just want to say at the outset, everything I'll show you is either experimental data or wind tunnel data. It's flight test data for the most part. So no simulation data in any of this. So that's the general idea. We'd like to try to characterize nonlinearity by using a linear approximation with slopes that can change with time. So next slide, please. So if I go up one dimension now, and I'm looking at now non-dimensional pitching moment, aerodynamic pitching moment, and that's called CM in the plot on the right side there. It's now a function of one of the controls, let's say, maybe stabulator, I'm calling that delta, and angle of attack again. And I'm still in only 3 dimensions here because that's what I can draw. And you see now I have a surface dependency. A nonlinear surface is wavy, but I want to characterize that nonlinearity of the pitching moment dependency on alpha and delta. And I can do that with approximating planes. In 2 dimensions, it's a plane, but when there's more than 2 independent variables, we call it, or explanatory variables, which there are in general because there are more than one control, etc., then we have what we can do the same thing. Can't draw it anymore, but we do the same thing, and we call the approximating planes hyperplanes. Right? So what we want to do is to characterize nonlinearity with hyperplanes that can change their slope according to where we are in the flight variables, or where we are in the space, you might say, the independent variable space, explanatory variable space. So, now this approach actually has what I call this approach has legs, and what I mean by that is that the latest and greatest methods we have for characterizing nonlinear dynamics are based on local linear approximations and the eigenvalues that can be computed from that. So if we have something that's continually finding what the best local linear approximation is to what is really a nonlinear dependency, that's something that feeds right into these nonlinear dynamic analysis techniques such as bifurcation theory and stability theory. So next slide, please. So now we get down to some details of how you do that. If I take now the pitching moment, and now I haven't non-dimensionalized it, I've kept it dimensional just for notational simplicity, really. But we could do it non-dimensionally, and in fact, it usually is. So, but anyway, I've got this is right out of the equation. The thing that I need is the pitching moment, aerodynamic pitching moment. And what I want to do is I want to characterize that in terms of linear expansion in things that I can measure, like angle of attack, pitch rate, and control deflection. And here I only have one control deflection, but there are many. So this is simplified in that sense also. And we also have at the right side there this character nu, which means that's the part that's left over, the part that I can't model with this linear approximation, which of course is an approximation. So each, one of the reasons I want to do this is that I'd like to have a functional dependency description in terms of things that I measure, like angle of attack and pitch rate, so that I can predict what the pitching moment will be. So that's my goal. It turns out that you can do this kind of modeling equation by equation, right? So individual equations, and here I'm just looking at the pitching moment equation. So what you can do, one approach to it, is to say, well, in that pitching moment equation, I know everything except for the aerodynamic forcing function. So I solve that equation for everything except that, right? And on the right side, I have measurements of alpha and q and the control deflections. For a modern aircraft, flight test aircraft, let's say, the data system can measure all these things at about 50 hertz. So that's 50 times a second I can get measurements for alpha and q and delta, and measurements for the left side because I have measurements of everything else in the equation except for the pitching moment. So I can write this equation down 50 times every second, right? But I've only got, if you look at that equation, I've only got 4 unknowns. So I've got 50 equations and 4 unknowns. It's an overdetermined set of equations, which I can solve with linear least squares. And that's the general idea of how to go about this. Now, of course, every second I get a new 50 points, or a new, maybe it's 2 seconds I use, a new 2 seconds of points, then I do it again, and I get different slopes. There are different characteristics. So, and these characteristics, the M alphas and the MQs and so on, are called stability and control derivatives, as a lot of you probably know. And they have physical interpretations. The M alpha, for example, is a static stability term. The MQ is a damping term. And the M delta are control power, control effectiveness. So the values of those quantities can be interpreted in terms of the stability and control of the aircraft. So that's the idea, and that the number of points, as I said, is much greater than the number of unknowns, and we can use linear algebra to do this, and you can do it in what they call one-shot solution. In other words, we don't have to iterate to get this solution. We can do it in one shot. So you might also note that what we're really doing here is using a multivariable Taylor series expansion and dropping all the terms that are nonlinear, right? Just using the linear terms. All right, next slide, please. So. Why would you want to do this? Aircraft system identification. I have several reasons here. There are more. But in general, one reason to do it is what we call flight envelope expansion. We have an aircraft that maybe is predicted to fly in a certain way, and we start out flying it in a safe region, you might say, and then systematically do testing, do the kind of analysis that I just explained to take a look at the stability and control characteristics as we move up in, let's say, Mach number or an angle of attack, make sure aircraft is okay to continue. That's very time-consuming, and it's usually done flight by flight and very carefully and very methodically. But system identification is right in the middle of that, of course, because that's how we analyze the flight data to determine stability and control. Also, these next few items here are just the 2 at the bottom are what we already talked about. They're simulation and control design both require models of the aircraft, and the models of the aircraft can be updated and made more accurate using flight results. And also we have another reason to do the system identification is prediction methods that are used on the ground, like computational fluid dynamics and even wind tunnel testing. We'd like to know after the fact how close those predictions were to what the aircraft actually does. And what the aircraft actually does is determined using these system identification techniques. So, next slide, please. And this slide is just to describe that it's not easy to do this for a number of reasons. One of them is that the aerodynamic dependencies are not simple, as I discussed before. They're multivariate and they're, in general, nonlinear. The forces and moments have to be inferred from the equations, and I also mentioned that in passing as I was talking about the analysis technique. If you're in a wind tunnel test, you can put a model on a sting and measure the forces and moments directly through a balance. In an aircraft in flight, you cannot do that, of course, because it's a free body flying in the air. So what we do is infer what the forces and moments must have been by measuring everything else in the equation except for the forces and moments, as I mentioned before. Measurements are noisy and imperfect, like they are in any experiment, and that's the equivalent of saying that we want to see the truth, but we have to look through a little bit of fog to see it. So that complicates matters, of course. The physical quantities cannot be varied independently. And again, looking back at a wind tunnel test, I can put a model in the wind tunnel and change the stabilator deflection without changing anything else. Right? And by that means, I can find out what the effect of the stabilator is. For an aircraft in flight, as soon as I move the stabilator, the aircraft pitches, the angle of attack changes, and so on. So you have a more complicated situation in that I can't move one thing at a time with everything else fixed. As soon as I move one thing, everything's in motion. So that complicates the experiment design. And further complicating it is that a lot of times you have aircraft with all-time feedback control operating, which essentially says I'm going to start moving the stabilator, for example, in response to pitch motion. Since the control law is doing that, it's actually correlating those variables. And if you remember back to the slide when we were talking about how we're doing the identification, I need to have all variables doing something differently so that I can tell which one of them is responsible for which variations in the pitching moment, you see, to get those influence coefficients. So this also complicates things, and also the atmosphere is not always still, and it's turbulent, and that can really be equated to an unmeasured input. So all these things make the problem difficult. Next slide, please. So that's my background, and I want to tell you a little bit about the history. One of the great things about working in this field is, in aeronautics in general, is the historical record is excellent. It's captured very well. And in fact, a lot of the reports are online, as a lot of you know. So back in 1919 at Langley Field, which was shortly after the charter of the NACA, the predecessor to NASA, they were doing flight tests on Curtiss Jenny aircraft. And they were looking at longitudinal stability and control in much simpler ways than what I've just described, but still very clever ways and using what they had very ingeniously, I would say. So I just wanted to put this up here so you realize that the aircraft system identification research is something that's been going on at NASA for a very long time, really since the beginning. Next slide, please. So since that time, really up to the present, there's a conventional way to do this flight testing for system identification, and that is on the ground, we design the maneuvers or make a flight plan of what we'd like to do, and the aircraft takes off. We have the pilot or perhaps a control system or computerized system execute the maneuver. We then come down, land the aircraft, and download the data and start analyzing. And inevitably, there's something that we'd like to do differently. We'd like to have a little more amplitude on the maneuvers. We'd like to have the frequencies be different. Maybe the pilot didn't get on condition quite right, etc. So there's always this feedback loop that we go back around, redesign the maneuvers, and go fly again. Now, part of the problem with that is that, as anyone knows who's done flight tests, there can be a long time between flights. There are things that go on, safety reviews, instrumentation calibrations, things break, and so on. People have to be scheduled to do the work and so on. And also on a research aircraft in particular, other people want to test on the aircraft. So it can be a long time. If you have to wait your turn to come back around, it can be a long time before you get this feedback loop and get some more data that you need. So one of the ideas that's come up is that why don't we put that feedback loop, which is necessary, put that inside aircraft takeoff and landing. In other words, let's do it in a flight while the aircraft is still flying. So now you take off and you have a maneuver that you start with, and then you analyze the data online and while the aircraft's in the air, and iterate with your redesigning the maneuvers, and don't land the aircraft until you're sure you have the data that you were after, you see. And this makes for a huge improvement in efficiency. especially for things like envelope expansion. So next slide, please. So one of the first projects to use this sort of idea was the Pathfinder, NASA Pathfinder. And this aircraft was a solar-powered aircraft, 99 feet wingspan, and it flew very slowly. It was a very flexible aircraft, as you can see from the picture, but it flew very slowly and had unsteady aerodynamic effects as well as flexibility. So one of the ideas that was come up with and was executed in this project was that why don't we do some testing while the aircraft is in the air, telemeter the data down, do the analysis on the ground, and then based on that analysis either change the control gains or continue with our flight tests with the control gains as they are. So this was done with what they call single-axis frequency sweeps, where one control at a time was moved first in a slow sinusoidal fashion and then progressively a higher frequency to get a wide range of frequency inputs to characterize the dynamics. And a spectral frequency response estimation method was used to do the modeling. So this was done every 10,000 feet for this aircraft. The aircraft took about 50 minutes to climb every 10,000 feet, so there was time to do this. The data was telemetered down, it was analyzed, people made the decision about the stability margins and the flight control tuning, whether the gain should be changed. That was dialed in from the ground, and then onward to the next point. And this worked very well, and in fact, the Pathfinder set a record of 71,500 feet. It was a record for both propeller aircraft and solar aircraft at the time, later broken by other aircraft, but this was a record at the time. So this was the first sort of approach to having the analysis go on while the aircraft was in the air. And it was feasible because this aircraft was very slow and climbed very slowly. There was a lot of time to do the testing. And next slide, please. So I'm just showing a little flight data here from that project. And the bottom trace is the one you should look at there. That is the frequency sweep that I spoke of, where we move one surface first into slow frequency and then an increasing frequency as it goes up, and then use what they call spectral estimation to identify a Bodie plot, you might say, or frequency response. But one thing you might know from this plot is that you need, when you use that method, it takes quite a lot of data to do it, to get good spectral estimates. And in fact, you see there's 90 seconds there. And that's 90 seconds for each input, right? So each control, done one at a time, right? Which is feasible on this aircraft, but we'd like to do things faster than that. So next slide, please. Another really landmark study or landmark project was the self-designing controller. This was an Air Force project, and it was executed by a company called Barron's Associates in Charlottesville, Virginia, and also by Lockheed. And the idea here was to use real-time stability and control estimation in a manner similar to what I described before to feed that information as the aircraft changed in flight condition, or maybe would change due to damage or a failure, and to feed that into a reconfigurable controller. And in this case, it was a receding horizon controller, they called it, and have that reconfigure the aircraft control to have it still be controllable and survivable. And one of the main points of this, or one of the things that made a big splash about this project, was that they were able to land the F-16 Vista with a simulated left stabilator failure. So left stabilator was stuck. They had their online estimation routine go through, figure out what the stability and control derivatives were, and reconfigure the control law, or feed that information to a reconfigurable control law to enable the aircraft to land. So this made a big splash in the field, where you could see that this kind of technology, see the possibilities of this kind of technology. Now, the estimation technique that they used was a time domain method, similar to what I described, but with constraints. And what I mean by that is they had a priori values of the stability and control derivatives that, and also some time constraints, some temporal constraints, which needed a bit of tuning to make that work. And also, that technique did not provide error bounds for the parameter estimates. So, but still, just an excellent project. And this technology was also used on other projects as well. It was used on an SBIR for the F-18 closed loop reconfiguration, and also on the X-40A project. So, next slide, please. Around 2002, frequency domain method for real-time parameter estimation was demonstrated on the Twin Otter aircraft at NASA Glenn as part of the NASA Glenn icing research. And this technique is a very simple one. It's one I'm going to try to describe here to you later on. It gives accurate parameter estimates and also error measures. So when we estimate these parameters like M alpha and MQ that I showed before, we like to know not only what the value is, but what the error bar is, how good that value is. Those are two important components of getting estimates for these things. So it gives those, and it's really the only technique that does that. It gives the error bars as well as the parameter estimate. The time domain techniques do not do that. And also, it's very robust to measurement noise and dropouts. And of course, when we're doing things online on the aircraft, there's no chance to fix dropouts or to smooth out the noise or filter the noise. There's no chance for that. So, and I'll talk more about this technique as we go on. Next slide, please. Later, at NASA Dryden, there was, as part of the F-15 SAVE program and also the IFCS program, Intelligent Flight Control System program, there were some experiments on what kind of inputs should be used for this real-time parameter estimation or real-time modeling. So I'll show some results from that also as we go on. Next slide, please. And now we come to the present time. We have at Langley subscale models of generic transports, and I'm showing them here. They're instrumented with research instrumentation. On the upper left, you see a single-engine jet, and the lower right is a twin-engine dynamically scaled jet. These are both jet-powered, remotely piloted aircraft. They're all instrumented with research quality instrumentation for angle of attack, pitch rate, everything, control surface deflections, GPS, and the entire suite. And this is as part of the safety program. These models are being flown at NASA. And let's go to the next slide, please. These models, as well as others, can be are associated with an infrastructure called the AirStar system. And the AirStar system is really the support and equipment used to fly these model aircraft. What's shown there is what we call the Mobile Operations Station, or the MOS, which is a truck that contains a control room, flight test control room. So, and it's a very state-of-the-art equipment in there, very, very intelligently put together. The MOS carries its own power source. You see there's a generator in the back. So we were able to operate these remotely piloted aircraft in various locations. It's a very mobile, very transportable type of thing. And the photos on the bottom you see on the lower right is a picture of the control room inside the MOS. And there's also a pilot station inside the MOS where a pilot can fly remotely. Fly aircraft remotely in the future. We're still working towards that. But this approach of using these subscale models, and it's very inexpensive for one thing, and you can and we've demonstrated that we can get good, high-quality research data. And for complicated problems like we're trying to solve, like aircraft that are out of control or high angle of attack, high rates, and so on, or real-time parameter estimation or reconfigurable control, we need to do a lot of testing because it's a complicated problem. We need a lot of data to solve it. And so this is a way that we can get that data within our budget constraints. And really, if you're talking about testing transport type of aircraft, it's really the only way to go to do the flight test because full-scale aircraft cannot be used for this type of testing for practical and safety reasons and also budget reasons. So, this facility has really been put together in an excellent way by the staff at Langley, I have to say. And it's really an experimenter's dream. And I know that from experience. It's just it's a great facility, and we get some great data out of that, and I expect some more also. So I'll show you some results for that from that using that facility later on. Next slide, please. So the uses of real-time models. Why do we want to use these? We already talked about the efficient flight testing. All right, we can get very efficient if we know that if we're able to estimate parameters online and in real time. We talked also about the adaptive and reconfigurable control, many of those techniques need real-time parameter estimation or real-time modeling. So to operate properly. Vehicle health and safety monitoring. What I mean by that is if I have an idea all the time of what the aircraft stability and control is, I can tell if the aircraft is degrading over time, maybe due to age, if there's a failure of certain types, and that sort of thing. So you can really use this technique to do the equivalent of providing stability and control measurements or stability and control meters in the cockpit to the pilot, because we've got these parameter estimates that are reflective of the stability and control which are updated at all times. This real-time modeling is an area that the more you think about it, the more ideas you come up with ways to use it. Because what we're really trying to do is have the aircraft at all the time have an idea what its own stability and control characteristics are. And there are a lot of things you can do with that, one of which is flight envelope prediction. It can be very useful for accident investigation also, if you have this kind of information. Next slide, please. So what I have on this slide is just a little description of a paradigm shift that you can entertain. If you had real-time dynamic modeling, you can change the paradigm, which is currently the following. We have one or maybe a few test aircraft that we test very thoroughly, and then we assume every other aircraft that's like that behaves in a similar fashion, no matter how old and whatever happens to it. If we have real-time modeling or real-time monitoring of the stability and control of the aircraft, we can change that paradigm to let's characterize every aircraft as it is for what it is at its own time, whether it's aging, it's damaged, something's a little different about it. We already know when you get to flight regimes like high angle of attack and high rate that very small changes in the geometry of an aircraft can cause very large changes in the response. So this kind of pushes us towards this method of let's characterize each individual aircraft as its own and have its own characterization of itself. And one of the things I just mentioned to one of my colleagues recently is that if you think about this, what I'm really trying to do is put somebody like me out of business because we're trying to get this aircraft to characterize itself, collect its own data, and have it so that we can tell a pilot to go fly this aircraft, do some maneuvers, or have the computer do some maneuvers, land the aircraft, and download an updated simulation of the aircraft. And that takes me out of the loop completely. So, which would be okay. Plenty of other things we could do, but that's one of the goals. So next slide, please. So I'd like to now talk about some technical challenges in pulling this off, and this being characterizing the stability and control all the time for full envelope flight on board the aircraft. So there are a couple things out here that I just wanted to point out that are the main problems at the moment. One is excitation, which I think we have a good solution for, as I'll show you. Another is data memory, which we don't have a good solution for at the moment. We need to work on. And some practical implementation issues, which I believe we do have answers for. So kind of a mixed bag. And of course, as all research is, you go along and you find more things that you need to address. But I hope I can transmit to you that what we have here is we're very close to the place where we could have an aircraft characterize its own stability and control all the time. So next slide, please. So I have here a couple of quotes from people that I admire a lot. One is Dr. Box, who was a professor in Wisconsin. And talking about experiments, and one thing that he said is to find out what happens when you change something, it's necessary to change something. Which sounds pretty simple, but you'd be surprised how often that comes into play. So what that means is that if I want to know what happens when the elevator changes or the stabilator changes, if that means I want that linear influence coefficient, I'm going to have to change the elevator to see what happens. So you can't just fly along steady and there are a lot of times when an aircraft flies along and nothing's happening. It's very in a steady state. When you fly across the country, for example, there's a lot of times when that happens. So you can't find out what these influence coefficients are unless you move something. Another quote that's good to remember while we were doing this experiment design is if it's not in the data, it can't be modeled. And that's Dr. Mark Tischler, who works for the U.S. Army out at Moffett Field. And what he means by that is that if I want to characterize a particular dynamic mode of an aircraft, then I need to do an experiment where that dynamic mode of the aircraft is exhibited. Otherwise, I won't be able to model it. So those are important aspects, and I think you'll see how they come in as I talk some more about what we're trying to do here. The other thing is that the good experiments require high signal-to-noise ratio, meaning that when we see that short period motion, let's say, or some dynamic mode, it better be big enough that it stands above the noise. Otherwise, we can't identify it. Right? That's one thing. And the second thing is low correlation. We can't have, we still have to move things to find out what their effect is, but we need to move that thing in a way that it's different from the way we moved everything else. Otherwise, we can't tell who's responsible. We move two things the same way, and we have a correlated response. We can't tell which of those variables influence that variation. So those are the two things. And so with those in mind, let's go on to the next slide. Let's talk about a conventional frequency sweep, and this will lead into the methods that we're actually using for these experiments. On a conventional frequency sweep, you have a control surface that you start with a low frequency, and you continuously increase that frequency until you get to the upper band of where you expect natural frequency of the modes to be. Right? So we like to excite the system right around its natural frequency to get good response, to get our signal to noise up so we can identify the the dynamics. The problem is we don't always know where that natural mode is or where that frequency is. If we did, we wouldn't have to be doing experiments, right? So this is one approach to doing that. One of the problems, though, is that we apply the frequencies sequentially. We start with a low frequency because at low frequency, that would excite a low frequency mode, which we need to wait a long time to see because it's a low frequency mode. It has long periods. So we start with the low frequency and then go to the higher frequency. Now, the problem with that is the low frequency oscillation sometimes moves you off your condition. So in our context of what we're talking about here, it moves you from the point that you started at to get that tangent hyperplane, tangent approximating hyperplane, moved you to somewhere else during the experiment. Right? So we don't like that. And also, since it applies the frequencies sequentially, it's not efficient because it just applies one at a time and they're sequentially done. And also, this type of input is for a single input only, and we know aircraft have more than one input. So you have to do this input for each input in turn. So, next slide, please. So one idea that has come up is why not take different frequencies, now not a continuous stream of frequencies, but let's take discrete frequencies, and let's add them all up and apply all the frequencies at once. And so that's what's shown here in just an example fashion. If I have three frequencies for the input, let's say I'm going to apply this to the stabilator of the aircraft. I've got a mid-frequency, a higher, and yet a higher one. And I just add those up, and I get, if I add them up just as they're shown there, I get the white trace on the right. You see what happens on the white trace is that sometimes the peaks add, sometimes they cancel, and I get, during that time series, I'll get large excursions. I don't like the large excursions because that tends to push me off my condition where I want to be. So one of the things you can do is you can say, well, I'll take each one of those sinusoids and I'll shift them in time relative to each other. In other words, give them a phase shift. And I'll optimize that phase shift so that the peak-to-peak amplitude of the result of adding them together is minimized. And if you do that, you get what's shown in the yellow trace there, where the peaks are all mashed down, and they're really mashed down to, to where they're approximately equal all the way across. And they are, in this example, they're optimized for that. So that's as low as you can go for this. So, and I might mention also that I've added three frequencies here. The difference between those large peaks on the white trace and the peaks on the yellow trace gets bigger as I add more frequencies, right? Because more frequencies means the peaks get even larger. So this is a very good technique to still get all the energy into the input, but not have these large excursions that start pushing me off my condition. I like to stay right around. I really want to stay around one condition and do my oscillations right locally to that. Next slide, please. So what I want to show you now is a clip from a flight test data. This is on the NASA 837 modified F-15 out at Dryden. And what they're running here is what is the equivalent of the white trace before, right? We just took some discrete sinusoids and added them up. And if you watch the background while this is flying, you'll see what I was talking about this moving off condition. So could we run the first clip, please?
Pretty good. Ready? Okay. There's 10 seconds. Complete. Start it up. Stand by. I think we can get one more if you hurry. After that, I'd show about 20 miles.
Okay. So what you saw there was a pretty, and enough you could easily pick it out. Trajectory change as he was basically moving off condition using those kinds of inputs. So next slide, please. So what we'd like to do instead is to have these optimized multisigns is what we call them, where we shift the phases of the individual components to each input, and we do that in a fashion that minimizes the peak-to-peak amplitude. Right, so we don't get these large excursions off our flight condition. And also, the technique can also be used in the way that I'm showing here on this slide, where if you have more than one control input that you're using, which we always do, and on this example is actually for the HyperX. This was HyperX experiment design that I'm going to show you in a minute. But what you can do is you can choose these sinusoids so that they're harmonics of one another. Right? So I have a whole set of harmonics, sinusoids, and if you remember from your math, harmonic sinusoids are orthogonal to each other in the time domain. So what I have is harmonic sinusoids that I'm going to apply to the three controls, and I use different frequencies for each control. By doing that, I have, in the time domain, since they're harmonics, they're orthogonal to each other. And also, that just means if I did an inner product of the two time series, I'd get 0. Or they're the most unlike each other as they could possibly be, is another way to say it. But since I'm using different frequencies, and those frequencies are, what I do is interleave the frequencies for the different controls, as I'm showing here in the plot. So the rudder is using the frequencies in the red, the aileron, the frequencies that are green, and so on. So in the frequency domain, it's also orthogonal. These inputs are also orthogonal because they're using different frequencies. So this type of input has really a great advantage that it produces inputs that are orthogonal both in the time and the frequency domain. So no matter which domain you use for the analysis, you still have orthogonality of these inputs, and that's very important so that you can assign the dependencies properly, as we talked about. So they're optimized to minimize the peak-to-peak amplitude, which is shown there in the bottom right. And then there's a measure of the input energy on the bottom. So we want lots of energy in, not too much amplitude excursions peak-to-peak. And the other thing I want to mention is that you notice when you interleave these frequencies that each input has a wide frequency band because they take turns in taking the subsequent frequencies, which are all harmonics of one another. And when you do that, if you just look at the rudder frequencies, there's a wideband input there. There's a wideband input for the aileron and also for the elevator. So the advantage of this is that you can design the input form one time and use the same input forms for different flight conditions because they have a wide frequency band. So if the natural frequencies float around inside that frequency band, it doesn't matter, you'll hit it somewhere with that wide frequency input. This is a big advantage for flight test programs because a lot of times you don't want to, especially if a computer is doing the input like happened here on HyperX for this problem, the computer does not have a lot of extra time and space to be doing computations for inputs. So we give them one sequence. We say, this is the sequence I want you to run on the rudder every time. This is, at the same time, run this on the aileron, and at the same time, this on the elevator. See? And then we only scale the amplitudes for dynamic pressure. It makes for a very efficient test. It's very brief because everybody's moving at once. We do the lateral and the longitudinal data collection all at once. And we have only one input form. So these inputs are really excellent inputs for system identification. And in fact, I mentioned to someone the other week, it's hard for me to imagine how they can get any better than this. It's really a very efficient input. So let's go to the next slide. I want to show you now how these inputs were used on HyperX during the descent phase of the flight. And next slide, please. This is just a picture of the mission profile for the HyperX. Now, I don't want to get into the details of that too much. I just want to show you this to give you an orientation of where these maneuvers were flown. The HyperX was carried to its flight condition, its test condition, by a combination of air launch from a B-52 and also a modified Pegasus booster, and then pushed off the nose of the booster at its flight test condition. The X-43 test, the HyperX test, was done for a scramjet engine validation, which worked, of course. But after that, the engine cowl closed and there was a descent portion of the flight. And during that descent portion, these maneuvers were flown for collecting data to do stability and control estimation in hypersonic flight regimes. And that's the part over there on the right of the trajectory where the hypersonic, during the hypersonic glide, we called it, these maneuvers were run. And it was the same maneuver sequence, as I said, to run all the way down for different amplitudes. So if we could run the next video clip, please. What I'm going to show here now is this is flight test data run through an animation because we don't have pictures of the HyperX in its flight. But what it's doing is executing this maneuver, which is elevator, rudder, and aileron working all at the same time in an orthogonal fashion. And you see what happens is the motion of the aircraft looks similar to what you might see if it was going through some turbulence. Right? And the advantage of this is that it keeps the aircraft on its trajectory and just bumps it around a little bit. So you can keep the guidance and control guys are very accepting to this type of an experiment because it keeps them on their trajectory, doesn't move them off the trajectory, but still you get this excellent flight data for characterizing the stability and control. So because of that, these types of inputs are also being used on the Air Force Falcon project for the same sort of reason. That you can stay on your condition and still collect excellent data. So let's go to the next slide. What I'm showing here are some results from the flight test data analysis on HyperX. And this is actually the data that you just saw animated. What we're looking at is the pitching moment, the non-dimensional pitching moment, which is CM. That's in the middle plot there. The data is the white line, and the model is the dashed orange line. And as you can see, the model that we identify, and the top line there is the elevator deflection that was designed in the way that I mentioned before. And you see that this looks like something like a random sinusoid. It's not random, of course, but it looks like that. Like a buzz on the surfaces is what I call it sometimes. So we buzz the surfaces. We did that for about 28 seconds or so, maybe less, and collected the data and did the modeling. And the modeling was, the experiment was so good that the modeling, as you can see there, the model matches the data almost perfectly. There's a value in the lower right there called R squared. That's a measure of the model efficiency, the modeling, the amount of the variation that's been explained by the model. It's 99% out of 100. So, and the bottom trace is the difference between the solid line and the dashed orange line. So you can see it's almost a flat trace of noise. I've told people back at Langley I may show these data, for the rest of my career, because it doesn't get any better than this. The experiment design was so good that the modeling results just came out terrific. So and it looks like, this is what a simulation case looks like usually, but this was all flight data. So let's go to the next slide. This was at Mach 5. Now, I want to say, too, before I go on, that was not a cherry-picked result. All the results were like that. They all did that well. One of the things we do also to validate that our models are good is try to predict for another maneuver where the input form was different. So if we have a model that predicts well, then we start believing that model is pretty accurate. So on HyperX, we had maneuvers following those sweeps that were of different form. They were square wave forms. And that's shown on the top plot there. The data is in white again in the model. Now the model is not using that data. It's using the model that was identified from the sweep before and trying to predict this data. And this maneuver was run later in time. So actually it's at Mach 4.4. The aircraft was losing Mach number as it went down very rapidly. And that value is even an average. The Mach, if you look at the Mach trace as the aircraft descended, it was just a straight line, and now it was decreasing continuously. So there's a little bit mismatch near the end, but that could be attributed to the Mach effect because the Mach is changing. By the time we got to the prediction maneuver, the Mach was different. But still did a really nice job of the prediction. So the point of all this is to show you that kind of an input is very efficient. It moves the aircraft off the condition very little. It's like a turbulence input. And it can be done on all the surfaces at once and for a very short time. And that's exactly what we're looking for to do this real-time parameter estimation. So next slide, please. Another issue is what I call data memory. And what that means is when something happens to the aircraft, maybe it's damaged, or even if it goes to a different flight condition, what you really have is a different aircraft. And so what do you do about that? You just say, I'm not going to remember anything from the past. I'll start over right now. Or do you say, I'll remember a little bit from the past. I'll just forget some of it. Or do I do something else? Do I say, well, I'll go back to what I knew from before, the last thing I knew from before? Or do I say, all bets are off, I need to buzz the surfaces right now to figure out what's going on? Right? All those questions, when to do that, when to buzz the surfaces, when to remember, when to forget, those things have not been figured out, and they have to be. But that's for future work. It's one of the things we need to do to make this a technique we can use all throughout the envelope. So, next slide, please. So here's some practical implementation issues I want to talk about. Let's go to the next slide. I'll go through all of them there. I want to tell you about this frequency domain method, which is very efficient in its computation. Gives you accurate parameter estimates and valid error bounds, as I was talking about before. We don't need to use constraints, as or using some other methods. And it's robust to imperfect data, which I'll try to show you. And finally, and also, this method is the one I'm most familiar with. It was another reason I'm talking about it. But it's also been evaluated independently for me or anyone who's associated with it at Langley by two different groups that were interested in looking at different real-time methods, and both groups came down on the side of this particular maneuver as the best to use, which I agree with. So let's go on to the next slide. So here's how it works. If you have some time history of, let's say, a control, that's shown on the top plot there, and it's just maybe a pilot input or a control surface time history. And what you do is you say, well, I want to project that time history onto sinusoids at different frequencies, and I'll choose what those frequencies are. In fact, I'll choose frequencies that are in the frequency band of interest, which is where I expect the dynamic modes of a rigid body to be, rigid body aircraft. And every time I do that, I can do what they call Fourier transform and get a complex number called a Fourier series coefficient. Now, normally that's done in batch calculation. But, so I'll show in the next slide. Let's go to the next slide, please. It can be done very easily recursively. And the way you do it is this. If you look in the middle there, the batch Fourier transform is essentially a projection of the time series that you're interested in onto a sinusoid. And the sinusoid is a complex sinusoid. It's e to the minus j omega t. And in batch, you would take the entire time series and multiply it point by point onto the frequency, the sinusoid, and get a number, and that number is the Fourier coefficient. But if you look at that summation and write it out, you find out that you could do that very easily recursively. But every time a time point comes in, you multiply it by the corresponding time spot in the complex sinusoid, and add that to what you had from last time. So you can do this, and this would really be called doing the Fourier transform the hard way. In other words, not using a fast Fourier transform. But what we do is say, well, we don't need to do all the frequencies when we do this transformation. We just want to do the ones that are in the range that we expect the rigid body modes to be. And, give a little extra on either side. So that's the trick. We do the Fourier transform the hard way, but we do it only for limited numbers of frequencies and right where we're looking, right where we expect these dynamic modes to be and where they really have to be. So, if you do that, you maybe limit your frequency band to 0.1 to 1.5 hertz or so. And if you use a discretization of 0.04 hertz, which we found to be pretty good, although it's not very sensitive to that, so that's 36 frequency points. So 36 frequency points for each signal, and maybe you have 10, 12 signals to do this. So it's not a lot of computation, really, to do that, to do these recursive transforms. And if you look at the recursive relationship at the bottom, it's really to update that transform at a single frequency. It's a multiplication by a known quantity, which is e to the minus j omega t, and an addition. So one multiply, one add, and that is updated for that frequency. Of course, there's 32 frequencies for each one, let's say. But that's still a very small amount of computation, and really pretty simple to do. Next slide, please. So so that would get the data into the frequency domain. A byproduct of doing that for the limited frequency band we're talking about is that you get rid of some imperfect data problems. And what I mean by that is this. If you look at the side slip angle trace on the upper left, that is a real flight data, and it has a dropout in it. As you can see the dropout there, one value where it goes a very large amount away from all the other values, and it's noisy. If you do a Fourier transform as I described and only use a limited band of frequencies, you get not only a cleaning of that noise, because most of the noise is wideband, and maybe there's some structural responses and so on. But that noise is discarded because it's actually not even computed, because when you do the transform into the frequency domain, those components, which are shown in the lower plot towards the right, those components are not even in the transform. They're taken out completely because I never even computed them. So it's an automatic filtering operation to use this limited frequency band. And it turns out also that when you do that, the effect of a spike or a dropout is also mitigated, as you can see. So what I've shown in the upper right there is after the transform. In other words, if I only transform for that limited frequency band, and then I go back to the time domain, the value or the equivalent of the time series that I'm using is up on the upper right, where all the noise has been cleaned off and the dropout has been removed. So, and all this happens just as a natural byproduct of doing this transform for a limited frequency band. So it's a nice way to approach it, and I don't have to do anything extra to get this benefit. Next slide, please. So now we're back to where we were before, when we're talking about the time domain modeling. This is really what they call a regression. We're trying to predict the pitching moment as a linear function of things we measure like alpha and Q. The only difference is now that I've taken all those time series that I was talking about before and put them all into the frequency domain for the limited frequency band. And one advantage of doing this is that even if I fly for 2 hours, I still have only 36 frequency bins, right? Because every time, as I go along in time, I keep computing the Fourier series coefficients and modifying the values for these 36 bins, you might say, for each signal. So even if I fly for a very long time, I still only have 36 frequency points. And the least squares modeling and everything else I said about the modeling before really applies the same way to this frequency domain technique. So, except for the fact that in the frequency domain, the numbers that you use, or the data, is complex. It's complex numbers because of the fact that we have e to the minus j omega t that was used in the transform. Okay? But other than that, that's a small tweak. You can still do the least squares problem the same way as before, practically. So, and what this does is allow you to get these stability and control derivatives. And you know, the other thing is when I do this problem now, I still have an overdetermined problem, but I have 36 data points because they're in the frequency domain for the 36 frequencies. So it's a very efficient way to do it, and it turns out it's very accurate as well. And if you get into the theory of it, what you find is that the theory is such that it matches what's happening in practice, and the error bounds that you compute for those unknown parameters, which are M alpha and MQ, are accurate, right, as opposed to not being accurate as they are for time domain. One other thing I want to mention is that when you do least squares modeling, the least squares technique always tries to minimize the biggest residuals that it sees, right? So large values get paid attention to quite a lot. In the frequency domain, those large values are dominant modal frequencies. That was exactly what we wanted to do, is to minimize the minimize the difference between the model and the data for that frequency. In the time domain, if you have a dropout, for example, the least squares technique is trying to minimize the difference between the model and that dropout, which is exactly what we don't want it to do. So that's another advantage of doing things in the frequency domain. So next slide, please. So I want to show you now a flight test demonstration. The optimized multi-signs inputs were run on the NASA 837, and although the data was not analyzed on board, this was not, the analysis that I'm going to show you was done after the fact on the ground. But we did that in a manner that was similar to what, we just ran the data through the algorithm as if it were on board. So let's go to the next slide, please. So this is not very clear, I don't believe, but what I'm going to show here is on the right side are traces of response variables and controls, and you'll see there have the characters like you saw on the HyperX problem there, these multi-signs. The bottom trace on the right is the stabilator deflection, and the top trace is angle of attack, and the middle trace is pitch rate. And then on the left, there are three of the stability and control derivatives. One is the vertical force due to angle of attack, that's the top plot. The middle plot is pitching moment coefficient due to angle of attack, or the M alpha we showed before, and the bottom is the stabilator effectiveness, or M delta S. Right? And the yellow lines are the values that were computed. If I take that data and I take it offline and use a nonlinear iterative method, the best method we have offline to estimate these parameters, that's the value that I get. Right? So I took this data, analyzed it with our nonlinear iterative method that we use, best thing we have on the ground, and we drew those lines. And now if we run the video clip, hopefully we'll be able to see what happens when you see the data is just going through in time on the right side there. And on the left, the dots that you see, or the markers that you see, are the estimates that this frequency domain real-time parameter estimation technique is saying those values are. And the error bars are 2 sigma error bounds. So I don't think it's real clear there, but what you see is on the left side. Let's go to the next slide. Maybe we'll see a little clearer. On the left side, you see that at the beginning, now this technique is run without telling the algorithm anything about the parameters. So it doesn't know anywhere in the real line, it doesn't know where to look for these parameters. It's got no information whatsoever. So after just a few seconds, though, it's figured out that where those stability and control parameters should be, and if you define where they should be as, the answer that the iterative nonlinear method gets when it sits on the ground and iterates through the data. And you see it only takes, maybe you can't see, but after only about 3 or 4 seconds, it's already figured out what those parameters are. And the rest of the time, it's just staying right on where they are, and it's not moving. So that shows you both the efficiency of the inputs, these multi-sinusoids, and also the fact that it just doesn't take the frequency domain method very long to lock in on what the stability and control derivatives are. In fact, one of the things we need to study is how long do these inputs have to be, and what amplitude. We haven't made that study yet, but you can see, like just from this, that it doesn't look like we need much past 5 seconds. And when you're talking about doing this modeling for something like dynamic motion, the short period motion, the period of that motion is about 2 or 3 seconds. So any algorithm is going to need to see about 1 period before it figures it out. So it's almost down at the minimum already, as it is. But we might be able to get even faster if we give it some what we call a priori help. In other words, instead of telling it, look at the real line and tell me where this number is, we might say, look over here. It might be over there, or over about -10 or so. Start there. And if you do that, then you can make it even faster. So let's go to the next slide. So for onboard computations, using the frequency domain method I described, one of the things that's, several of the things that are nice about it are, for the number of frequencies that you select, those number of frequencies are fixed, as I said. Even if you fly an hour, it's still 36 points. And that keeps the computations way down. The recursive transform is very simple, as you saw. It's a multiply and an add for each frequency, for each signal. And you can do it for any selected frequencies, the ones that you select. So you can, we've been talking all about rigid body dynamics and everything, but if I decided I wanted to do a different problem or a more complicated problem where we're looking at structural dynamics, I could just shift the focus of the frequency transform to a different frequency band and look at that instead. The computations on board can be done at a lower rate than I showed for rigid body stuff because, we might have 50 hertz data on board the aircraft. But if we're only looking for frequencies down about 1.5 or below, we really don't need data any faster than maybe 10 hertz or 20 hertz. So that means, let's say it's 10 hertz. That means I can use every fifth point that comes in to process through that recursive Fourier transform. That makes it even faster because I don't have to process every point. So it's very efficient at very low memory and computational requirements, as I talked about. And then we also talked about how it's imperfect. It's very good with imperfect data, which when we're flying, we don't have the chance to correct that data. So next slide, please. So I want to move on now to current NASA research in this area. And one of the things we're doing as part of the safety program is doing Airstar flight tests. And with the what we call the S2 aircraft, which is shown there at the right, as I said, fully instrumented aircraft. And we're using that aircraft and the Airstar system infrastructure to study real-time methods for efficiently updating full envelope aerodynamic models. And as I mentioned, it's a very efficient way to do this. We can do lots of flight tests when the model runs on kerosene, 5 pounds of kerosene per flight. Still have to pay for the people and all that, but it's a lot quicker. The turnaround is very rapid. We get the data back in a few minutes after the flight, to analyze and look at it. And of course, with real-time methods, you get the answers right away if that works. And I'll show you that here in a minute. And another research thrust we have under the safety program is an NRA agreement with the University of Tennessee and also with Burl Applied Research, and also with NASA Glenn. And that research is aimed at trying to use real-time parameter estimation in icing conditions. And the main problems in icing conditions is, for example, you don't want to necessarily buzz the surfaces when you're in icing conditions. And also, icing conditions tend to be associated with turbulent air. And we know already, I mentioned in passing, that turbulent air is a problem because that's an unknown input. Right? So that's a very challenging problem, but we have an excellent team in place to do that. We've got an ex-NASA pilot and icing research experts from NASA Glenn, and so we really have I'm working on that also. So we really have a nice team, I think, to make progress there. So next slide, please. What I want to show you now are some flight tests from the Airstar program on the S2 aircraft, which is shown there in the picture. And I'll note also that this flight test was done last week. So last Thursday is when we took this footage. So let's go ahead and run that video. All right, throttle check. These are just general shots of our operation and the ground crew getting the aircraft ready to fly. There's what they call a UAV runway at NASA Wallops to be used for this testing. That runway is right next to the shoreline. Now, at the present time, we're flying these aircraft with as RC control. There you see the RC pilot with his RC transmitter. But we're moving towards actually flying this from inside the MOS or inside the truck. We have synthetic vision displays that were just checked out last week and look to be very, very accurate and looking really excellent for that. We're still trying to work towards that. And there you see a picture of the pilot station and the synthetic vision. Now, during this flight, we did had the pilots do some maneuvers for system identification. They were just doublet maneuvers. We just told them to bump the stick longitudinally and also for the rudder and the aileron. You see, you did a very nice job on the landing there. These flights go about 7 minutes or so, but in 7 minutes you can get quite a lot of data. That's very surprising. You do a lot of maneuvering. So, what I want to show you now is some data from those flights, and this is so let's go to the next slide, please. And this is in a format similar to what I showed you for the F-15, but the difference here is that what I'm showing you now is what was shown to me at my workstation in the MOS inside the truck while the aircraft was flying. In other words, we had the real-time parameter estimation and real-time dynamic modeling software running in real time. The data came down from the aircraft through the telemetry system that's operated by the MOS or by the truck. That data was sent over an Ethernet connection to a laptop right next to me, and running this algorithm in real time. So, and I'll note also that it was doing that. So we're doing all this data collection and the plotting that you'll see here, and I still had to slow down the laptop to do that. And it still had, I was doing this at 50 hertz, and it was taking only a small fraction of that frame length to do it. So we still had plenty of time in the computation. So as before, what we have here on the left side are stability and control derivatives. I believe it's on the top there, m sub alpha, and the middle one is mq, and the last one is m delta e. So those are those same parameters that we talked about when we were talking about the frequency domain and the time domain modeling methods. Then on the right, you'll see from top to bottom angle of attack, pitch rate, and the elevator deflection in degrees. And I want to mention, too, that we're shown here just these longitudinal results, but the results were being computed in all the axes. So there are many other, that's why if you see on the left there's our pull-down menus. I can select any number of any of the stability and control derivatives and show that trace, but I only have one trace to show you here on the video clip. But it works for all of all the derivatives at the same time in real time. So, and the other thing I want to mention is that, because it worked in real time, everything I'm going to show you in this next clip was done as soon as the aircraft landed. The thing that was not done was drawing that yellow line. I had to go back and take that data, reanalyze it using our iterative nonlinear optimization technique to draw that yellow line, so you can see where the right answer is, you might say. All right, so let's run the clip. So you see the pilot just implements just a simple doublet. And he did that following that, he did that on the rudder and also on the aileron as well. Right. I don't know if you can see, but the estimates at the beginning start off, and they look a little closer at the start than they did before. The reason for that is that we actually turned on the real-time estimator before we told the pilot to do these doublets. So in his natural maneuvering, the system actually got pretty close to the right answer, even though he was not doing any maneuver specifically designed to collect information for the identification. So it's a very encouraging result. You see that after the doublet starts coming in, the difference between the final answer and the answer obtained with the batch estimate is almost the same. And those error bars come down as you get closer to the answer. So the important thing is that this technique not only gets the right answer, you might say, but it knows when it doesn't have the right answer. Right? So if it's off the right answer, it knows that, and it gives you a larger error bound. And that's critical because you don't want to, when you're doing especially real-time reconfiguration of the control law, you need to know, or updates of the onboard modeling, you need to know what data is good and what data is not good. So the error bars are really critical for, as I said before, the frequency domain method is really the only one that does this. So that was really a very encouraging result. The first time, to my knowledge, the first time that the real-time parameter estimation has been done in multi-axes, actually in real time, and of course also on a unpiloted model. So, next slide, please. Oh, and so here, this is just the final slide that I was talking about before. So. Okay, so let's go on to the next slide. So finally, in conclusion, I have just some very general things to say. We've come a long way with the real-time modeling, and I hope I convinced you that we have some good practical applications for it. The real-time modeling is really a very key part of the safety program, both for reconfigurable control and for vehicle health monitoring, vehicle health management, I believe it is. We've made a lot of progress, but we have a lot of things to do yet. We have to solve the data memory problem that I spoke about, and that really has to be done with sort of an information management executive, you might say, on board the aircraft. It takes a look at failures and takes a look at the information it has from the real-time estimator, flight condition, and so on, and determine whether we need to buzz surfaces right at this moment or whatnot. Other things as well, we have demonstrated this for specific flight conditions. And the flight condition you saw actually for the S2, the last one that I showed, was actually pretty high of attack. But they're all still in the envelope that you would expect what I'd call normal flight operations. So we still have to see that this can work in places where the operations are not normal, right? Higher angles of attack, near stall, high rates, and so on. So all that has to be worked out as well. And we also, finally, we have this method that does a really nice job of getting us a local linear approximation to what is really a nonlinear dependency. And it changes its orientation as we go, as I mentioned. But what we'd like to do is to fold that back into some onboard global modeling of the aircraft so that it can update its global model of what it thinks this nonlinear dependency is and carry that on board the aircraft. So you can the aircraft eventually could carry its own idea of how it behaves. And that's the ultimate goal. And once you have that, then all kinds of doors open up. So that's what we're aiming for. And the current NASA research really is aimed at achieving that all-weather, full envelope real-time dynamic modeling. So can we have the next slide? I have a couple of people to thank. And I want to tell you about this also. These are a couple textbooks that came out last year. My colleague, Dr. Vladdy Klein, and I wrote the one on the left. And Dr. Mark Tischler, my friend out at Moffett Field, wrote the one on the right with Robbie Rempel. They use quite a different approach to modeling out there. In California, they use a spectral estimation technique that I mentioned with the Pathfinder aircraft. But both these textbooks come with software. Our textbook has a MATLAB toolbox, which is essentially the toolbox that we use at NASA Langley to do flight tests, data analysis and modeling. One of the techniques in that toolbox is the real-time parameter estimation technique that I talked about here. Also the experiment design technique that I talked about is also in there, as well as many other things. So that's a MATLAB toolbox, and it's a public release software. It comes with the textbook as a download. So, and that's got really excellent reception in the field. Now the book on the right also comes with software. It's a student version of a commercially available software called Cypher that they use at the Army with the U.S. Army out there to do a lot of work on rotorcraft and mostly rotorcraft, I would say, but also fixed-wing aircraft as well. So I want to mention these because I feel like these are really the two first books of this kind to come out specifically for aircraft system identification. And we feel like if you look at these books, read what's inside them, that's really a good representation of the state of the art for aircraft system identification. So next slide, please. I had a lot of help for this talk. This is sort of my network of system identification guys. They are both inside NASA and outside of NASA. And every one of these guys helped me in some way to put together this talk, so I appreciate all their help. If you go to the next slide, the guys on our AirStar flight test team are really excellent professionals. They're really a joy to work with. A lot of real experts on this team, and they did just a bang-up job of getting this AirStar facility in shape and ready to go. And we're getting research quality data out of it, and they just did a tremendous job. It's really, as I said, it's an experimenter's dream to sit in that moss and be able to do what we do. So I thank all of them, and they also helped me with some of this. And finally, the next slide, I had graphics help as well from our graphics team at NASA, which they were very excellent. And Kathy Barnsdorf and her group did our video for us. So next slide. That's all I have, and I'd be glad to try to answer any questions you have.
Thank you, Dr. Morello. I'm J.D. Harrington. I'm going to handle the question and answer portion of today's presentation. Before we start, if you would, make sure we get the microphone to you and identify yourself once you get there. Also, for our center viewers, if you would like, by all means, if you're in a central location at your center, step up. We should be able to handle your questions as well. To start off with, any questions here from headquarters? All right, one here in the front.
I'm Murray Hirschbein from NASA headquarters, Fundamental Aeronautics. One of the big values on this seems to be when an aircraft is damaged or behaving badly and trying to gain control. If you had a control surface that was erratic and behaving badly, where you have a significant nonlinearity, how does that affect the number of frequencies or your convergence rate? Or the number of frequencies you have to use to get convergence and your convergence?
Well, that's really largely unknown, but what we do know is that we can make the frequency band big enough that it would very likely incorporate that. Right? So that's kind of the philosophy. You don't get much, there's not much downside to just including extra frequencies. Because what happens is, let's say you included too many frequencies. Well, the frequencies that are high, that there was no response, come out to be zeros and they're not paid attention to by the estimator. So in theory, what you could do is make the frequency band very wide. The downside is that requires more computation, and that if your band is, if there's nothing happening out there, you're wasting your computation time. That's the only thing.
Capture it well when this is an erratic behavior on the part of the control?
Well, it captures a real-time estimate. So if it's erratic behavior in that it's time varying, then yes, it'll capture that because it keeps updating its idea of what the stability control is. Now, if it's chaotic, then we've got trouble. But if it's just something that's erratic and changing in time, it's actually designed to do exactly that, to accommodate something that changes in time, as well as being nonlinear. So that approximating linear hyperplane is accounting for both of those things, both time varying and for nonlinearity.
All right, thank you. Any other questions here at headquarters? All right, we have one here in the back.
I guess just elaborating on what I think Murray was trying to get to, is there any theoretical result that leads you to believe that if you depart from a nominal flight condition and you create a linear model at an off-nominal condition, you're eventually going to be able to recover a nominal flight condition?
Well, that's a control question. Right? And so, so I'm probably not the best guy to ask that to. But what I can tell you is that I can get you a characterization of it as it departs, assuming the information is there. And that's another thing. I mean, I'm not going to say we got that all solved. That's not solved. But, the way to solve it is to have aircraft that you can depart and that you can measure things on. And we have that with the Airstar. We've got an aircraft we can depart and measure things on, and we can get at that kind of answer, which we don't have right now. And, it's hard to get that answer because you've got to depart an aircraft to do it. And you're never going to depart a full-scale transport, of course. But you can depart these RC models.
All right, if I'm not mistaken, I believe we have a question from Glenn.
Yeah, my name is Hendricks. I have a question for you regarding controls. In the engine simulations, generally speaking, we can pull most of the sensor plugs into our modeling except for throttle position. So you can still control the engine on the basis of throttle position. So the question I have is, how many sensors can you afford to lose and still have control of the aircraft, and what are those sensors?
Well, that's a very good question. I kind of have to fall back on the answer I said before, which is, my expertise is in the modeling and not in the control. Now, once I, determine what a model is and pass that along to the controller, that's another department, if you want what I mean. But as far as the modeling goes, if you say, well, I'm going to lose my alpha sensor, what does that do? Well, what that tells you is you can't get any alpha derivatives. You cannot get M alpha or anything else related to alpha. So it's really that's a critical loss in terms of the modeling for sure. So, and of course, all that applies to the other things as well, the controls and the rate derivatives. But if your question is about what's needed to control or recover the aircraft, that's not a question that I can answer.
All right, any other questions here at headquarters? I have a few questions here, one of which is interesting. You spoke about using models for local aerodynamics, which involves estimating stability and control maneuvers and parameters. What about using the so-called black box mechanisms and models such as neural networks and that?
Right. Well, neural network model, it's just another form of model. And the problem with neural network models, in my opinion, is that usually you have the structure of the model is arrived at in an ad hoc fashion. Because of that, a lot of times it's an over-determined or it's over-parameterized models. And those type of models we've known for many years give poor predictions. So that's one thing. Another thing is that, you know, an important part of having a model is to get some insight from it. If you have something like a black box model, like a neural network, it's hard to get your head around what it's actually telling you. If you have a parameterized model, like one of the ones we talked about there, we can relate every one of those parameters to something physical on the aircraft, its stability, its damping, and so on. You just can't do that with the parameters of a neural network or any other black box model. And finally, when you do the parametric modeling, which is what I talked about, you can have error bounds. You can compute statistical error bounds and know how good that model is. You can't do that for neural networks because of the way it's where the parameters are, the way the structure of the model actually is done. So I guess the bottom line is I feel like there are a lot of really good ways to model things. There are things that have a lot of advantages over neural networks, and neural networks have little of any advantages over the standard methods. So that's what I would say.
I have one more question while we wait here at headquarters. How do you see real-time dynamic modeling helping to improve aviation safety?
Well, you know, one way to do it in the near term is to do what I sort of mentioned in passing, is that, you know, aircraft, commercial aircraft now, most of them have data buses where the data, all this data that I was talking about, all those quantities are measured on board the aircraft at 20 hertz. That's plenty of rate to do what we were talking about here. That is, figure out what the stability and control of the aircraft is. So it wouldn't be much of a stretch to have this on a commercial aircraft. You know, you have to remember what we're talking about here is a passive system. I'm not moving any controllers. I'm just figuring out the current stability and control of the aircraft. So it's taking data from sensors that are already on the aircraft, data that's already on the bus, and processing it and telling it, the pilot, according to what I'm measuring right now, your stability is such. According to what I'm measuring right now, your elevator effectiveness is not what it should be. Right? This is what we're aiming for with the icing project, where, you know, you can do that kind of calculation and notify a pilot. All you're doing is notifying him that your elevator effectiveness right now is reduced. So you need to pay attention to that. So, and you know, for many icing accidents, for example, that would be enough. Just to alert the pilot there's something wrong with your elevator effectiveness, do something about it, or, you know, descend, or, you know, apply your anti-icing systems that are on board the aircraft. So I'd say that'd be the near-term thing. You can really put the equivalent of a stability and control meter inside the cockpit to help pilots know how their aircraft is behaving, the current stability and control health of the aircraft. Now, of course, I've been advised by my pilot friends that you can't put up a plot of M alpha and expect the pilots to understand what you're talking about. But you can certainly put up green and red bars and say your stability is good, or your you know, control effectiveness is good. And then, you know, in the long term, you know, all the reconfigurable control, many of the reconfigurable control methods require real-time parameter estimation, real-time modeling. So, and that, of course, that's in the far term, because now we're talking about something that's going to modify the control law, something that's going to move the surfaces that needs to be certified, and so on. So, but all those things, you know, and also the aging of aircraft. You know, if you have something on board the aircraft that's always keeping track of the stability and control, you know, you can identify, you know, if your aircraft is getting so old that the elevator effectiveness is degraded. You know, so.
All right. Any other last questions? All right. Having none from the field either, we'll conclude today's presentation. I'd like to thank Dr. Gene Morelli from Langley for his time and his team's efforts. If you have any other questions about this project or any other aeronautics research portfolio from our portfolio, give us a call. We can try to help you out. You can also go to www.aeronautics.nasa.gov for further information. Thanks.